Good morning, everyone. My name is Zahra Miri. I'm a PhD candidate at University of Waterloo in Ontario, Canada. And today I'll be presenting evaluating early-age interlayer bond development in 3D printable concrete using ultrasonic testing on behalf of my co-authors, Dr. Aurelio, Professor Mariana Polak, and Professor Hassan Bash. Here's a quick overview of today's presentation. So in this room, I'm sure you're all familiar with the concept of 3D printing and its advantages over conventional processes, but it also introduces new challenges, particularly related to layer-to-layer interfaces. So air voids can form within the interface, weaken the interlayer bond, they can cause anisotropy in the mechanical properties, and they can negatively affect performance, safety, and durability of a structure. The main factors that affect the bond between layers are the time interval or the delay time between the position of layers. This is directly related to the surface moisture. A higher surface moisture can provide a better fluidic environment for the layers to adhere, and this is also affected by some other parameters related to the printing process or the mix design itself. Now the question is, how can we evaluate the bond between layers? So there are generally two methods, destructive mechanical testing, which I have an example of this kind of test which we use in this research, a splitting tension test, and non-destructive testing or NDT methods. Another example of ultrasonic testing is shown here. So destructive testings can give direct values for the bond strength, but they also have some limitations. Like after each test, the specimen is damaged. The test is time consuming. There are limited number of specimens can be tested, and also they might not be suitable for in-situ monitoring during printing. However, NDT methods will give, after each NDT method, the specimen remains intact, and it can give like indirect bond quality indicators. It's fast, it's repeatable, and it can be suitable for real-time or in-situ monitoring of 3D printing. So among the NDT methods used for concrete, ultrasonic pulse testing or UPD is the most widely used one because of its simplicity, portability, and repeatability. In this technique, high-frequency sound waves are transmitted through a specimen. While they're being transmitted, if they encounter any like interlayers, air voids, or cracks, they might get reflected. And then by analyzing the received signal that comes out of the specimen, we can like find out what's happening inside. Here are some parameters that can be obtained from the results of a UPT. The first one is ultrasonic pulse velocity, which is the distance that a wave travels divided by the time it takes. The other parameters can be signal amplitude and energy, or some frequency domains features, which I will talk about it when I'm showing the results. So with this being said, this research had three main objectives. Firstly, we wanted to see which ultrasonic parameters can help us to detect weak interlayers. We wanted to see if we can correlate ultrasonic parameters with mechanical bond strength, and also we wanted to assess interlayer bond development from day 1 to 7 and investigate the effect of missing the interlayer on improving early-age bond strength. This slide shows how we prepared the specimens. We used a commercially available 3D printable mortar. The specimens were cubes with a side of 100 millimeters. I should mention here that rather than printing the mix, we decided to cast the 3D printable mix into molds into 2 layers. The reason that we did this was that at this stage we wanted to limit the number of interlayers to 1 only, and if we wanted to make this a specimen by 3D printing, then the dimensions of the specimen would be kind of limited by the dimensions of the nozzle size and would give us like a very small specimen, and then ultrasonic measurements would be like an appropriate method. So that's why we chose to cast the 3D printable mixer mix design into the molds. They were mixed using an MTEC mixer. And we had 3 types of specimens, no interface, which were cast monolithically. We had dry interface, which were cast in 2 layers with 1 hour time gap between the cast. And during this 1 hour, the interlayer was exposed to air. And we also had wet interlayers, which were made same as the dry ones, but before pouring the second layer, we misted the surface with water. The specimens were demolded after 24 hours. They were tested at day 137, and in total, we had 45 specimens, which 15 per day, 5 for each group. This slide shows the setup for the test that we conducted. On the left, we have the splitting tension test, and on the right, we have the ultrasonic pulse test. So a wave is generated in the pulsar, is amplified, and then sent to the specimen by a transducer, and then received by another transducer and recorded by the oscilloscope. The frequency of the transducer that we used was 150 kilohertz. The reason, again, of this choice was based on the dimensions of the specimen, the average velocity of sound wave in concrete, and the location of the interlayer, which was at 50 millimeters. Before going to the slides, to the results, I wanted to show how generally the received signals from the ultrasonic looked like for day 1 and day 7 for different type of specimens. The specimens that had no interlayer are shown with dark blue, and the dry ones are shown with green, and the wet interlayers are shown with red here. The first thing that can be seen is that at day 7, the signals got stronger for all the specimens. I'm comparing these 2 values. And the specimens that had interlayers had weaker signals at both days, and also a greater decay rate. This slide shows the results for the mechanical destructive testing, which we did like splitting tension test. At each day, at all days, the specimens that had interlayers, whether wet or dry, had significantly less tensile strength compared to the cast monolithically specimen. Specifically at day 7, the difference between the strength was around like 42%. And if I want to talk about strength gain over age, the specimen that had no interlayer had a strength of 2.1 MPa at day 1, then it dropped to day 1.7 temporarily, and then again it increased to 2.75 at day 7. So the reason this happened for these kind of specimens, I think it was like either because of microcrackings due early curing, or because of maybe a misalignment in the test setup itself, because like the splitting tension test is really sensitive to like surface flatness or any misalignments. Other than that, the specimens that had interlayers, the interlayer bond increased steadily from day 1 to day 7, and in average, they had 60% higher tensile strength at day 7 compared to day 1. And these specimens all failed at the interlayer. And regarding the effect of misting, it only had a modest improvement at day 1. The strength of the wet interlayer was around like 9% higher than the dry one. This improvement decreased at day 3 to 5%, and then to 4% at day 7. So I would say, like, although it could help like to rehydrate the surface initially at day 1, but its effect diminished over time. Now we have the results from the ultrasonic pulse test. The first parameter that we looked into is UPV, or ultrasonic pulse velocity. So the value of UPV increased with time, with curing age, which kind of represents like the progress of hydration, and like more continuity in the microstructure as the specimens are hydrating. But if we look at the different type of specimens at each day, there is no significant difference between the UPV of a cast monolithically specimen and the interlayered ones, and we had maximum like 3% difference. So I would say, like, although UPV could capture, like, could show the strength gain over time, but it wasn't effective in detecting like the weak interlayers. There was also a positive correlation found between UPV and the splitting tensile strength. This was moderate for the specimens with no interlayers with R2 equal to 0.63, but it was weaker for specimens that had interlayers, and it had an R2 equal to around like 50%. The next parameter that we looked into was the first arrival amplitude attenuation. This attenuation is kind of a ratio between the first arrival amplitude of the the received signal over the transmitted signal. So here we can see with age, the attenuation decreased for almost all specimens, which means that the signal transmission got stronger, and there were less like discontinuities in the specimens at like with age. And if we also compare like different type of specimens, we can see that at all days the specimens that had interlayers had significantly higher amplitude attenuation. This amount at day 7 was around like 40%. So I would say like amplitude attenuation could detect weak interlayers in the specimen. There was also a weak decreasing trend seen between amplitude attenuation and the splitting tensile strength, but this wasn't like, the correlation was not strong enough to give us a clear relationship. We also looked at the signal energy attenuation. Like, this kind of shows how much of the signal is dispersed inside the specimen. Again, from day 1 to 7, this energy attenuation decreased, which shows less energy dispersion and better signal transmission, stronger signal transmission, and also the specimens that had interlayers were performing again weaker, and it kind of represents a lot of energy was reflected. So far, all the parameters that I showed from the ultrasonic testing were obtained from the time domain signals, which shows that how the wave changes over time. But we also wanted to know which frequencies exist in the signals. So we did this using the fast Fourier transform, or FFT, which kind of takes the time domain signal, compares it to sinusoids of different frequencies, and records how much of each frequency exists. This is an example from our own research. It's for a specimen with no interlayer at day 3. The time domain signal looks like this. When it's transformed using FFT, we have the frequency domain, which has a spectral format. And from this, we found out the dominant frequency, or the peak frequency of this signal, was 154 kilohertz, which is close to the transducer that we use, and also the magnitude is given. So we try to find these two values for all the specimens at all days. The dominant frequency for all the specimens were between like range of 150 to 160. This stability shows that there was no major shifts in the frequency domain results because of, for example, immaturity of the specimen or any interlayers. However, when we look at the magnitude of the dominant frequency, again in a form of attenuation, we can see the differences between the interlayer specimens and the specimens that had no interlayers, and also we can see that the magnitude got higher as the specimen cured from day 1 to 7. And this is like almost for all specimens. So FFT gives us some frequency domain features, but it assumes that the frequencies are stationary, which means they won't change with time. But we also wanted to see how each frequency evolves over time, and this can be done. This was done using the continuous wavelet transform, or CWT. Like FFT looks at the signal all at once, but CWT tries to look at it piece by piece and compare it to short oscillating wavelets and record frequencies and time at the same time. An example of a 3D CWT, again from one of our specimens with a dry interlayer at day 7, is shown here. It can be seen that the dominant frequency here happened at this time, which is 83 microseconds, and it had like this magnitude. So on the left, we have like the scalograms for specimens that were tested at day 7. The color here shows the intensity, or like the magnitude of the frequencies at each time. And the red circles here are showing the dominant frequency, like 150 kilohertz, for different type of specimens. Starting from the top, we have the scaleogram for the interface for the specimen with no interlayer. As can be seen, the peak frequency here is concentrated. It happens early in time, and also it's stronger. But if we look at the specimens which had interlayers, like dry one and wet one, we can see that they are not concentrated, like they are more reflected, they have a delay, they happen later, and also their magnitudes are smaller. And I also gathered all the data for different specimens at day 7. The dominant frequency for specimens that were cast monolithically was between 40 to 44 microseconds. Then it was increased to delay to between 70 to 170 microseconds for specimens that had interlayers. Also, the magnitudes are significantly less than the case that we had no interlayer. So I would say CWT could help us to see the differences between the specimens. So now I want to present the main conclusions for this research. We found out that UPV rose with curing age, which reflects hydration and densification, but it showed little sensitivity to interlayer presence. Amplitude and energy attenuation decreased with age, and were able to distinguish interlayered from monolithically cast specimens, unlike UPV. Frequency results showed no shift in dominant frequency, yet magnitude attenuation was higher in interlayered specimens, which indicates greater energy loss. CWT analysis could effectively capture energy degradation and delayed arrivals, confirming its potential for detecting weak interfaces. And also, we found out that missing the interlayer improved early age bonding modestly, but the benefit diminished by day 7. And lastly, I can say that with careful data analysis and interpretation, ultrasonic testing can be a reliable, non-destructive tool for detecting weak interlayers in 3D printed concrete. And for future work, we want to repeat the process on specimens that were printed through 3D printing process that contain multiple horizontal and vertical interlayers. And also, we want to work on changing the interlayer condition, for example, playing with the open time, decreasing it or increasing it, or improving the bond, for example, using bonding agents between layers. Lastly, I want to thank Professor Giovanni Cascante for his help and guidance, and also my supervisors, Professor Mariana Polak and Professor Hassan Baj. I also want to thank my colleagues in my research group and at the Structures Lab of University of Waterloo, and also at the Non-Destructive Lab for their assistance and support. And thank you for listening to my presentation, and I'd be happy to answer if there are any questions.